So we are doing the basic foundation before we go to the bigger steps of panel data econometrics. Panel data. The word panel also implies longitudinal data. And what we are going to do is we are going to look at the basics before we build up into the heavy tools. So you see that unlike the mathematics we've been doing for the cross section, at this beginning, I will not be doing a lot of mathematics at all. But when we get to particularly dynamic panel models and a lot of other two-bit panel models, pro-bit panel models, and that is when we'll bring a bit of mathematics into the picture. So let's remind ourselves of some basics. Cross-sectional data, time series data, and panel data are three different kinds of data sets. A cross-sectional, you are focusing at a single point in time. You can decide what that point in time is. It can be a month, it can be a year, it can even be a day. But the key point about cross-sectional data is that you ignore the time element. Your focus is on the individuals. And the individuals can be a country, a person, a household, cities, countries, all of them. So ordering doesn't matter when it comes to cross-sectional, but ordering matters when it comes to time series. The time series, the individuals is not the focus, but the focus is on the time. So there can even be one individual and you are looking at it from different time. So you can look at UK and you can look at the inflationary trends of UK every single month over the past 20 years. That is a time series data. A panel data is a combination of both cross and time series data. It has to do with both individuals, which is I, as well as time dimensions. And you're going to see that is the best kind of data one can have. But there are two kinds of panel data. You have panel that is balanced, you have panel that is unbalanced. We'll look at that. Let's look at the difference between the two. So in a panel data, you have I, which is an individual specific factor, and T, which is a time specific factor. The I starts from 1 all the way to N, the T starts from 1 all the way to T. It is balanced if the same observations are appearing at the same time. So if you have 20 countries, 20 time periods, from the year 2000 to the year 2019, 20 years. And the number of, say, banks that you are looking at are say 30 banks. And all of the 30 banks are appearing every year. It means that your data is balanced and therefore your observation is how many? Your sample is balanced, your observation is how many? Godwin, are you there?
Oh, Doc, sorry, I missed out just a little.
So your observation is how many? When you have 30 samples over a 20-year period, balanced.
Okay, so 30 by 20, that's about 6,000 observations.
600. Okay. So now you have a 600 observations.
Yes.
Okay. And that is a balanced panel. However, an unbalanced is where in one of the years, some banks exited, some banks were liquidated, some banks were merged. So there was a lot of consolidation. So in some of the years, instead of it being 30, some of the years there were 24. Some of the years there were 30, 29. Some of the years there were 15. Okay. In that case, you still have a balance, you still have a panel data, but the data is not balanced. And there are methods that can deal with both situations. All right. So I've indicated that the panel data are very, very useful. One of the advantages of the panel data is that you are increasing the data sample. So you are reducing the case of dimensionality here. Remember that the case of dimensionality is when the number of individual independent variables are more or even close to the number of observations. So if the number of independent variables are 10 and the number of the sample size is 10, the chances of falling into the case of the dimensionality is very high. But as you increase the data sample, what it means is that you are cutting down that problem. You will not fall into that case. And that case can also bring about a lot of multicollinearity. So when you have a larger sample or larger observation, it cuts down issues about multicollinearity. That is why you will notice that when we come to panel data, we don't try to correct for multicollinearity a lot. It's not a big issue, okay, especially with large samples. Now, even though you are correcting for multico, it doesn't mean that you are going to handle heterogeneity, because there are still heterogeneous samples. Some of the banks could be state banks. Some of the banks could be foreign banks. Some of the banks could be private domestic banks. So there's a lot of heterogeneity in the data, and that can also affect the results by virtue of the heterogeneity. In other words, size matters, and you got to capture the element of size or deal with heterogeneity in the data. One advantage of the panel is also the fact that it gives you more information, because there are some questions you cannot handle when you're looking at time series or cross-sectional data. For example, the effect of some actions, some treatments, some controls, the dynamic relationship between some policies. For example, there could be a policy that was introduced in 1983. You will not know the greater impact of the policy until you collected a panel data. So once you collect a panel data, you will now be able to detect the effect of the policy better. The panel data is very useful. You can control for unobserved heterogeneity, whether it is time heterogeneity or individual heterogeneity. I'll explain that. So let's assume that you have taken a sample and you want to look at the impact of experience of a worker on the salary of the worker. Or you want to look at the impact of the educational level of a worker on the salary of the worker. So you've collected data on salary, you collected data on experience, you collected data on education level. And then you realize that the educational level positively affects that of the salary. However, there is some sort of unmeasured ability. You see, an individual may have some unique ability that will make that person be able to handle that IT aspect of the work, not because of his education. Not because of his education, but he has some unmeasured talent. But it's very difficult to measure the talent. That's why he didn't collect data on the talent. He's got some coding skills that he learned, but you did not take into consideration that coding skills. That becomes an individual heterogeneity or an unobserved factor, which is unmeasured, which can affect the behavior of the dependent variable, but you did not capture that into consideration. Now, the good thing about panel data is that it can help to control for that. You see that in the practical example. According to CL, panel can give you a better prediction than cross-sectional. And we know that because, again, you are looking at a lot of information from the past. And so it helps you to be able to predict the future better. You can also deal with non-stationarity. You can handle issues about measurement errors. Okay. And you can use it for a lot of dynamic dependent variable analysis, especially when you want to say, suppose you want to predict the probability of a customer defaulting his loan. The probability of that customer defaulting is a predictive analytics model. And you want to use that to be able to capture them. So this is a typical example of a panel data, as you can see. It's all there. Look at 1988 all the way to 1990 here. And then you pick the next one. Okay, so this is 1988 to 1990. Then you pick the next one again. That is also 1988 to 1990. Pick the next one, 1988 to 1990. So you will notice that the number of time periods are 11, and each observation appears in each time period. This is a typical example of the effect of price, consumption, and on the GDP. Let's take another example. If you look at this very example, it's an unbalanced panel. You still have the 1988 to 1990. You still have the 98 to 1990. Okay, 98 to 1990. But then in some of the years, you don't have consumption values. In some of the years, you don't have. So what this means is that now there are three ways you can handle this thing. You see, this very one here, you can do interpolation using the structure of the past. You can do interpolation based on moving average. You can do interpolation based on other, average that one can use. And then that can help you fill in this data here. Interpolation is very easy. I'll show you that. Or because of the situation, now some people would want to delete this whole lane. Okay, you are deleting everything. Now, whilst you are deleting because you don't have this information, you're also throwing this information away. So whichever one that you think you can defend it, that is when you do. But the key point is that at the end of the day, there is an unbalanced situation here. So you can remove that and still go ahead and run your work, recognizing the unbalancedness. So these are the two kinds of data. Now let's get into the few basics of panel data. Before the panel data, okay, let's recall what a cross-sectional data is. This is a cross-sectional data, as you can see here. This cross-sectional data is indicative of the fact that you have, just a minute. Okay. It indicates that you have a dependent variable, which is a function of an independent variable, a regressor. You have the error term, and then you have the intercept or the constant. It's something that will be used in all this one. The time series, the difference is that you have a subscript of t, okay, following the individual variables, whether it's a dependent or independent variable. You have a time of t. And the time is from 1 to t, where t is the total number of time periods. A panel is a bit different. Okay? The issue about endogeneity can be present in all of this too. And when we say endogeneity, there are several aspects of it. One of them is the situation where the regressor is correlated with the error. Which regressor? This one, which is the xt, it has some correlation with that of the u, the error term. Now, why is that a big issue? It's a big issue because one of the assumptions is that the errors, the independent variable, are not supposed to be multicollinear, which means among themselves. Okay, so experience should not be, correlated with education. Okay, and it can be that your experience could be correlated with education or the other way. For example, suppose you are told that once you've had 5 years of experience, your company will send you to go and do your master's or PhD. So it means that your PhD is dependent on your 5 years of experience. That word dependency is multicollinearity. So there is that sort of dependency there, the interrelationship, serial correlations there. But with the errors, you see, in the case of education and experience, you know the education is there. You know experience is also there. So that issue about, serial correlation is visible. It's visible because at least you can see the correlation. But then when the independent variable, say education is correlated with the error, the error, you don't see it. You don't see the error. So that is a big issue, and that is the endogeneity issue. If only you could see the error, then at least you could use some, structure to eliminate the errors. But you don't see it. And because you don't see it, that is uniquely not exogeneity, is not, multicollinearity, is not heteroskedasticity, but it is endogeneity. Now, there could be other ways of endogeneity, like I said. For example, when you have a dynamic model where you are taking the lag of this dynamic model. So if you have this dynamic model, you decide to now take the lag of this dynamic model. Okay. If you take the lag of this dynamic model and include it here in the independent section, that past data of y, which is yt minus 1, can affect y. And because the yt minus 1 can affect y, that makes a relationship between the y and itself, because it's just itself, but in the past. Okay? So that is also considered as an aspect of endogeneity. We'll look at that when it comes to dynamic panel data. All right. So let's go to the assumptions of classical linear regression model, because we are going to see which of these assumptions are corrected under panel. These are assumptions. One is exogeneity. Exogeneity is a very simple assumption. It simply says that the errors, okay, the expected value of the errors is equal to 0. Okay? And then the correlation between the errors is 0. In other words, there's no correlation between the error and then the regressor. Any covariance structure between the errors and the regressor should not be there. In other words, there should not be dependency between the error and the independent variable. It's a very, very powerful assumption. But watch the first one. The first one says the expected value of the error given the dependent variable. So you see, at this stage, you've held the dependent variable constant. That is 0. But look at the next one. The next one, so that's why this is a weak exogeneity. This next one says the expected value of the error with the regressor should be 0. So now it's no longer given. So if this assumption of exogeneity is not there, then we have what? We have endogeneity.
Okay.
And when you have endogeneity, forget about blue. The best linear unbiased estimator is no longer there. And then there is inconsistency in the beta parameters. The next assumption, which we know already, is homoskedasticity, sometimes called homogeneity, which says that the variance of the errors should be constant. If it is not there, we fall into the trap of heteroskedasticity, which will cause the beta parameter to be inefficient. Then there is autocorrelation. The assumption is that there should be no autocorrelation. Autocorrelation is when the covariance between two errors, not between an error and an independent variable, but between two different errors. In that case, when they are correlated, when they are dependent on each other, some way, we have a serial correlation, autocorrelation. Okay? And if it is not there, it's good. But if it is there, then there's going to be a problem. If serial correlation exists, then inefficiency of the beta parameter exists. Then there is this major issue of endogeneity, which we don't want to happen. So see, the whole idea of we don't want this, we don't want this, we don't want this means that if it is there, you got to correct them. That's it. The covariance between the error and that of the independent variable should be 0. There must be strict independence, 0 covariation. We know about collinearity. There must be no perfect collinearity. There must be no specification bias. Okay? We need to ensure normality, linearity. These are the basic assumptions. And we've indicated that whilst this one exhibits strict exogeneity, weak exogeneity, you can have a strict exogeneity in panel. The strict exogeneity indicates that the expected value of the error, but this time, the error term across individuals and across time, not just across individuals, but across individuals and across time. Okay? Given the dependent variable, and remember the dependent variable can be many as well, should be 0. So strict exogeneity considers both the error in time, the error over time, and across individuals. But then weak exogeneity considers just the errors across individuals. Okay. What can you do to correct heteroscedasticity? The last time we looked at it, okay, there are several ways. One way is by using heteroscedastic consistent autocorrelated standard error. You can use that. Okay. There was a common one, West standard error, that could be used to correct for that. But another way is that you can estimate a GLS, feasible GLS, or weighted least squares. You can use that to correct for either in a cross-sectional, Okay. Now, in a panel, you can also do that. In a panel data, you can also do that. But the form of GLS in a panel, and you'll learn this very soon, the form of GLS that you would have used for the cross-sectional, when we come to panel, this is known as a fixed effect and the random effect. So it is those fixed and random effects, they are the kind of the panel data version of the cross-sectional GLS that we know. But when it comes to endogeneity, none of these things can solve it. For endogeneity, you've got to now move into instrumental variables, either two-stage least squares, generalized method of moment, or the Lubel approach. Okay. So let's look at how to understand panel data generally, general panel data. So this is a typical general panel data model. YIT alpha plus XIT beta. This beta is a transpose of the beta. You have the errors here, which is UIT. Sorry, okay. Now, YIT, you can note that the error here, watch it. Watch the term here. The error is IT, okay, which means that it is changing across individuals and across time. But this error is a composed error. So you got to decompose the error. Okay. And when you decompose the error, you get these terminologies. The first one here, we talk about it, is the individual specific effect. The second one is the time dummies, or the time specific effect. That's a lambda t. And the epsilon IT is the actual idiosyncratic noise. Okay. The true random error, the true unobserved heterogeneity. These two, the individual specific factor and the time specific effect, these two are very important, and there are ways to deal with them. So basically, this is a general panel data. Let me give you a typical example. Suppose you are running a DEA productivity study, and you've estimated efficiency scores here. Now, you indicate that the efficiency scores that you've estimated is a function of some independent variables. Let's say the efficiency score of some countries. and you use some input and output to generate the score. You now have the score. But then there were some factors that can affect the performance of each country, but you didn't capture them in the input and output. So now you are doing a regression to capture those factors. And those are called the Z variables here. And those variables become the independent variables. In fact, sometimes we call them exogenous factors or contextual variables. Those variables are there. However, these variables, there are some other factors that can affect the efficiency scores, which have not been captured. So just like this, you can also have the individual specific factors, the time dummies, and then finally the error time. So this is a typical example of a panel data model. It's nice to learn how to write a panel data model, generally like this, and specifically when you have a model. Okay, everything that is here, I've already indicated it, the parameters involved. I want you to know that the term parameter or estimator is different from estimates and coefficients. What's the difference? What's the difference?
I think the parameters are the variables or the predictors, and the estimates are the beta values.
Okay, so the estimates are the numbers, the estimators are the Greek letters. So the estimators are the unknown. The estimates are the known. Okay. I've already spoken about the independent variables and what it captures and everything. Note that the composed error is an independently identically distributed, it's usually that, okay, independently and identically distributed with a zero mean and a constant variance. It is just like the cross-sectional one, but just that it's decomposed in this context. You can assume strict exogeneity of these errors, which means that they don't depend at all on any of the individual regressors, which means that that aspect of endogeneity is solved. That is why this is strict exogeneity. But there are three kinds of regressors or predictors or independent variables. The first one are those independent variables that are varying. They are changing across individuals and they are changing across time. Take, for example, the annual income of people. People's annual income are always changing. Okay, so if you look at your income this year, it will be different from your income next year. So it's changing. Your income is changing over time. But also, if you take me, my income is different from your income. Even though our incomes are both changing over time, our incomes across individuals are also different.
Yeah.
That is a varying regressor with an XIT. The next regressor is a time invariant regressor, sometimes called time constant regressor. So as the name sounds, when it comes to time, it doesn't change with time. It's constant with time. It's fixed, sometimes even called time fixed. But is it changing with individuals? It's varying. So by the way, this can also be called time varying regressors. It's the same thing. Sorry, what do you call it? Individual varying regressors. Okay, so this time invariant regressors are individual varying regressors. In other words, they are varying across individuals, but they are fixed over time. A typical example, okay, is gender. Well, generally, we are speaking based on where we are. Okay, general. That's why I use the word general. Because depending on where you are, it's not the same. But even if it's in a different country, it doesn't change immediately over yearly. You see, these changes, we are talking about yearly changes. So I don't think that a person will change his gender every year. Generally, people don't do it. So gender is fixed across, what do you call it? It's fixed over time. So over time, it's not changing, okay? But it differs across individuals. Okay? It differs. The gender in the world is not one. It differs from person to person. Race is another thing. Okay? You don't change your race every single year. Your race is changing between individuals, but it doesn't change over time. Generally, I'll put a question mark on race because in the example I'll show you, you will see that we will change race over time. Also, education. Education can change over time, but it can also not change over time. Okay. I'll give you an example. Once a person has started work, sometimes they will not go to school again. So at that point in time, the education will be what? Fixed. But it is also possible that after the person starts work, every year the person will want to go and do further courses. In that case, the education is changing over time. So that's why I put a question mark also on education. But these are all time varying, individual varying regresses, or time fixed, or time constant, or time invariant regresses. Now the last one. The last one is individual invariant regresses, which means they are time varying regresses. The terms can be quite confusing. Take, for example, the GDP of a country. Okay. The GDP of a country is changing over time. But then the GDP of that country is not changing across individual. For that country, it's not changing across individual. So that's a typical, most macroeconomic factors are individual invariant. So suppose you are assessing the performance of some banks. Because all of the banks are located in one economy, in a country, the banks are the individuals. So that inflation is not changing across different banks. The inflation is changing over time, but it's fixed across individual banks. That's a typical example of individual invariant or time varying regresses. I'm sure you get a point.
Yeah.
Okay. So the last thing about the element we saw is the unobserved heterogeneity. Okay. Those disturbances that affect the behavior of the independent variables over time. Okay. It has no time index. Okay, so it's assumed to be constant over time. It can capture the characteristics that are not picked by the individual regressors. For example, I told you about the ability of a person, even culture. So sometimes you do something, the behavior of the bank is improving. The bank's performance is doing well, but that is because of a culture. There's some element of a culture in the bank that is making the bank perform well. It's difficult to capture that. You cannot go and look at the culture of every bank. So you cannot capture that, but it is affecting. That's why it's unobserved. That is why it is something to deal with. Those latent unobservables can affect. So religion is a typical example. You can sometimes, you look at some people, based on their religion, the way they are aggressive is different from some other people. Yeah. So all of the, for example, suppose you want to determine the probability of giving birth. You will notice that the women are the ones with a higher probability of giving birth than the man. So in this case, it tilts towards the woman. It's very difficult to capture some of the things. It's very difficult sometimes to even capture race. I'll give you like tribe. Okay? Which people do you think can kill a lot among the Ghanaian tribe? While some people may have their opinion, nobody knows what's happening. So again, these factors can influence the behavior of some other people, are difficult to capture. Then there is the symmetric time trend. These are factors that are time varying. Okay? They have to do with regulations. So when the government brings about a regulation, a macroeconomic event, a COVID-19, an Ebola outbreak, any of these things can affect the behavior of some of the dependent variable. Okay. So you have to allow for those time elements. Okay. And normally they are contemporaneously exogenous to the conditional error. You can look at it from, so sometimes you want to capture the entire time dummies. You want to capture them as dummies. And then use it to see whether they affect the result. So sometimes you see a person will run a model, and then after running the model, the person will have model 1, model 2, model 3, model 4. And that is because he is capturing some elements in some of the models than in some of the other models. And he wants to.
I think I was looking at the paper yesterday on corruption and then economic development. Yeah,
okay.
Economic growth. So in the model, they capture the time that is 2000, 2001. They have to see which year the corruption is significant in.
Exactly. So you will know that corruption is significant in a particular, in other words, particular year is affecting corruption. And you see, sometimes during election, a lot of people, the month towards election or election year, people are careful to be corrupt.
Yeah.
But right after election, people are not careful to be corrupt because they have more time. Very good. So you can create a dummy from that. Finally, there's error term. Okay. That can be created. So this is a typical example of a model. This is a paper that I once published in Geneva Papers. And you will see that some of the variables are changing with time, some of them are not. So you can see that GDP is something that is changing with time. What you see here is a productivity index for insurance companies. And this productivity index for insurance company is affected by life, whether the company is life or non-life. Now watch this. You realize that I did not bring the intercept. And that is one thing that you want to know. The intercept is usually absorbed into the errors. So for real true panel data model, when you are formulating, majority of papers don't bring the intercept because it's perceived to be inside the error term. All right. Now, if you look at some of the variables, they are changing with time. Some of them are not changing with time. For example, GDP and inflation are both changing with time. When you look at a variable like regulation, the regulation is also changing with time. But for this model, I'm thinking that maybe this one should have changed only with individuals. Because whether the company is live or non-live is sort of fixed.
Yeah.
It's sort of fixed. So it should have been I alone. Okay. But that's a clear example of a specific panel data model. All right. Now we are going to look at how to implement the basic models of a panel in R. In R, not in another package. So I'm going to use the the Excel data that I gave you. And I'm going to run it here. Let me show the screen. We are opening the Excel file. You see the Excel file?
Yes.
So this is the wage band data. And you will notice that I'll give you a bit of story about the whole data set before we continue. So this data set is already a published paper by a very, very powerful professor. Okay. There are two professors who they are called Vela and Biebeck in 1998. They published this paper, and the title of the paper is, and this is like you writing your paper or writing your thesis. And the paper title was, Whose Wages Do Unions Raise? By the way, it's nice to understand this word union. So, you know, when you're in a company, there could be a union formed by the company, like National Union of Ghana Students. You get a point?
Yes.
And the idea is that unions are very useful because when you belong to the union can fight for your right, isn't it?
Yes.
So the question was, the unions, whose wages, if they agitate for the wage, are they increasing the wages of those in the union or increasing the wages of both those in the union and those not in the union? Do you get a point?
Okay. Yes.
So they postulated a dynamic model of unionism and wage rate determination for some young men. That's one thing you want to note. For some young men, not young men and women, but for some young men. Remember, the paper was in 1998. So the number of firms, the number of individuals were 545 full-time working youth males. Now watch the word. They are youth, but they are what? Working. And the sample is from 1980 to 1987. The data is actually from the National Longitudinal Survey youth sample. It's right there as I speak. That's why I got it. Okay. So the question is that we know that your wage, your salary is determined by some factors. The question is the salary also determined by belonging to a union or not belonging to a union? Of course, there are other factors as well. Now we're going to look at all of those. I'm sure you get the idea.
Yes.
Now, this is a balanced panel because every single individual person is captured over the 8-year period. So how many observations do you think we'll have?
So 8 by 5 or 5.
Yeah.
5.
So we have
4,360.
That's it. So that's the number of observations we have. And how many, and you can see that. So how many samples do you have?
The samples were on 5 or 5, but observations are divided by 8, making 4,000.
Exactly. I'm only asking you the question. I know you have already provided the answer, but I wanted to know that the difference between the sample and observation is that the samples over time make up the observations. All right. Now, how do we go ahead? We have some few things we want to look at. Okay. The nature of the data. The youth have just completed school. So by 1980, they have finished school and they have been working from that 1980 all the way up to 1987. So when you look at the data, which you can see here, if you take the first person, that first person is given an ID of 13. So that person is given all of this ID of 13. And that 13 person, the year is from 1980 to 87. Okay. The age of that person at that year is year 0. Well, the key variables that I'm interested in for us to look at are the ones highlighted in green. So by the end of 1980, that person has got how many experience? 1 year.
1 year.
By 1981, the person has 2 years of experience. And by 87, the person has 8 years of experience. Whether the person belongs to a union or not is a dummy. So you will notice that in the first year, this 13th guy was not belonging to a union. After that, he went into the union. He probably didn't like it. And so he decided to drop out of the union completely. Do you get a point?
Yes.
His ethnicity, I'll tell you some of the ethnicity variables. So let's put it this way. Let's get some few things first. The ages in 1980 are from 17 years to 23 years. Remember, these are just people who have graduated from college. So most of them are between 17 to 23 years. They entered the labor market recently, and so they have an average of 3 years of experience at the beginning of the sample period. So by 1980, they have about 3 years. Some will be less, some will be more. And these are the variables. I was talking about ethnicity. So the ethnicity indicates whether the person is Black, Hispanic, or other. And you can see that the 13th guy, he was other, which means he's neither Black nor Hispanic. Now, whether the person is married or not, you have it there, yes or no. So you can see that throughout the sample period, the 13th guy was not married, isn't it?
Yes.
He wasn't married. However, the number 18th guy was married by the time he entered the labor market today. Most of the data are here. Now, the educational level of the person is also shown there at the time of entering the labor market. The experience of the person. Yeah.
So in such instances, say marriage, for example, if it's all no across, is that variable relevant?
No, it's not no across. So see someone
No,
yes.
I'm asking yes. I mean, if the data is no across the sample taken, does that variable become irrelevant?
Oh, no. Not become irrelevant at all.
Really?
You just have to still analyze it. To determine its relevance or otherwise, you have to run. Because see, these variables could be interacting with other variables you don't know.
Okay.
Yeah. And the way they will behave may behave as a result of the inclusion of other variables in the data set. So it's the running of the data that will determine. Unless you were doing a simple regression and then with them alone, then in that case, I'll agree.
Okay.
All right. Next. The experience is there. The experience square is also there. Remember, this is experience. How many years? Then we took the experience square. You're going to see why. And then you have the wage. This is a wage. And then we took the log of the wage, which is L wage. You will also know why. Yeah. And then you also have the time dummies. So what we've done is that we created a time dummies for each time. So if you look at the 81, we start from 81 because the 1980 is a baseline. So if you look at 81, they will all have 0, 0, 0, 0 because, like I said, we started from 1980. But if you look at for 81, the 1981, for this first guy, that guy was there. So the dummy value is present. And then for 82, you see that it's present, and then on and on and on. So that's a bit of a feel of the data set. Okay. There are other things, but these are the main thing of the data set. Now, when you look at the original data set, there's a lot of sectors that are involved. Okay. Here is some research questions to address. Has the return to education changed over time? By the way, what do you understand as return to education?
The gain from education.
And what is that? Is a wage. Is a salary.
Okay. Okay.
So the question is, has the salary changed over time? That's the first one. Second one, what is the effect of unions on wages? You remember this was one of the questions we want to address.
Yes.
How does this impact of unions on the wage, how does it change by worker characteristics? And there are several worker characteristics there. What are the key forms of worker heterogeneity, generating the endogeneity of the union wages? Our goal is to address that. With what form of economic sorting behavior in terms of union and non-union employment are the data consistent? We'll check that too. So these are some sort of questions that I want to look at. Now let's look at the variables that are changing and the variables that are not changing and why we made some of them so. Which variables do you think are varying regressors? Okay, so let me just go to the Excel. Which ones do you think are varying regressors? They are changing.
So I think that income should change, salary should change, well, wages.
Yeah, wages. What else?
It should change. Yeah, the experience.
It appears experience is also changing.
It's time.
Sorry?
Okay. So when is changing, experience should change.
Okay. It appears experience is changing. It also appears that another variable is changing. Education. Well, no. No, not education, because education is past record. But basically experience.
Yeah. Experience.
Because at this stage, education is constant.
Yeah.
Okay.
Experience.
Now here, there was a mention of marital status and union. You remember the union status, there were some changes there. One guy was that and it changed his union.
Yes.
Yeah, so union too is possibility. Now married, yes, because some of them may not start as married, but over time they'll start as married. Look at this. You see one of the students was not married. Okay, 4 years into the work, he's gotten money. So he wants to settle down. And I think that's the same thing you want to do. Confirm or deny. Okay. So these three things are presumed to be time varying regressors here. in this very example. And the reason why experience is going to be part of this is because these are young workers and their experiences are rising by 1 year every year. So it's going up. Other variables that you think might be fixed are not fixed. Other variables that you think are not fixed are fixed. For example, race doesn't change over time. But here, both education and experience are set to be fixed. Why? The reason is because if they are all increasing their experience by 1 year, then it means that that is more or less like experience is the same every year. Doesn't make sense. Like, we are all increasing our experience. So among us, experience hasn't changed. Because experience is changing deterministically. So education may not be exactly fixed, but it might be roughly constant over 5 years. Because over the 5 years, the student may not necessarily want to leave the school, with scholarship or something like that, and then go and actually work. So we introduce education as fixed, but we will interact it with the yearly dummies. Okay. Now, the other variable is gender. So gender is obvious that if it was here, it would have been fixed.
Yeah.
So keep that all in mind. Now let's look at another thing. Some variables have been logged. For example, when you look at the data, you have taken the log of some of the variables, like the log of wage. Why would you do that?
Well, perhaps the values will be different across. We want to normalize them so that
practically, why will you do that to price? Practically, wage, because the wage here is the nominal wage. So when you deflate it, you get a real wage. So you got to take the log, because taking the log helps you to normalize, helps you to bring it to the real level. The wage is not important. What is important is the purchasing power, isn't it?
Yeah.
And that is why you take the log. So if you want the thing to capture proper, you take the log. You take the log. All right. So the point we indicated here is that since the deflation factor for 1987 is the same for all the individuals, we can use the nominal log of wage or the real wage. The difference will be simply absorbed in the intercept term. The logs will convert the changes into percentage changes. And you will see that, I think we did it the last time, when you are interpreting those with logs.
Yes.
We interpret them using percentages instead of using the levels.
Yeah.
So why log the wage? Because real wage is seen to be the proper reflection of the actual wage. All right. Now, some of the variables have to be you have to take the square. For example, we have experience square. Why?
Exhibit. Non-linearity where it could
Exactly.
rise, point, and then fall.
So it exhibits quadratic nature of the experience. You see, especially when you look at footballers, their experiences will rise, it gets to a point, then it starts falling, isn't it?
Yes.
It gets to a point, then it starts going down. And this is a typical example of why we need to take the log of variables. But see, the thing is that you don't just get up and we take a log, take a log. What you do is that you analyze each of the regressors individually. Okay. So you will notice that this variable, which is experience, we have been able to take the log of it. Yeah. And we've said it here. There's a beautiful video on how to check for parsimony and normality and linearity. I'll put it here, you can check it later. But the key point is that if you want to identify non-linearity, you have to use theory and think. Because you don't just get up and then take the log of everybody. I take the log of those that can be taken. Sometimes you have to even specify some non-linear models using polynomials and other things to handle the quadratic nature. So sometimes this is why you have to run models, different models first, to check if they are found. All right. Now we are ready. I will not include interaction term or predictive terms, individual predictors. Suppose there are two predictors that may be multicollinear. They are both trying to affect the dependent variable in such a way that they are no longer multiplicative, but they are additive. Okay. In such a way that they are no longer multiplicative, but they are additive. In that case, we have to measure them. Sorry, in that case, they are not multiple. Okay, in the case where they are not additive but multiplicative, okay, in that case, we interact them.
Yeah.
What is the difference between interaction? Richard, I don't know if you are here. Okay, could you explain to us the difference between interaction and multiplication of variables? Interaction term and then what did they have? Mediating, interacting terms. Mediating variables and interacting variables.
Yeah, so with a mediating variable, it's quite different from the interacting. And I will speak first on the interacting variables. That is where you want to check the multiplicating effect. So it's more or less you are multiplying those variables, checking when you multiply or you check the two effects at the same time, how does it react or response in terms of its relationship, its explanatory power. So the variable, you have a dependent variable being, let's say, the I don't know, income. Let's take it income.
Yeah.
Or let's say experience. You are regressing experience on wage. So you want to explain how experience actually translates into one's wage. And then you have this other variable, which I will assume for it to be what can I use for an example? Length of no, what? Age. Let's say age. So you want to know combining, you are checking the combined effect of one's age and level of experience. If you check that combined age, that's two variables, how does it explain? So does age actually lead to an increasing incremental effect in that relationship? So you, in the initial stage, you establish that, okay, experience leads to an increase in age, but an increase in wage. But if you bring in age, does age matters, or does age leads to more incremental results? That is when you have that kind of interaction. That means you are multiplying.
Okay.
And then with that of the mediating, okay, so with the mediating effect, you're more or less trying to say, does it serve as a channel in more or less in the presence of it, in the presence of that variable, does your results hold? Or in the absence of that variable, does your results, probably you do not get a significant result? So that is the basic explanation of it. So when you look at the interaction, you're looking at the incremental effect of it in the presence of that variable. However, with the mediating, you want to say, okay, in the absence of this variable, you do not observe any relationship, or in the presence of this variable, then the relationship exists. So you're trying to say that that variable, serving as a mediating variable, is the channel through which you can explain the relationship. I don't know if
Gordon,
I'm
do you
making
get it?
Yes, I got that.
Okay,
Yes.
what do you get?
So the interaction is to multiply, and then the mediation is to see whether X has a role to play in maybe Z causing, or if Z has a role to play in X causing Y, or in the absence of Z, does X have a relationship with Y?
Okay, so using the models I've written, how will we be able to use the models I've written to explain them?
Okay, so Y equal to the constant plus beta 1, x1, x2. So the first model is an interaction. Second model, the second model is Y equal to alpha plus beta 1x plus beta 2 x2. The second one is a regular regression model. Third one, Y equal to lambda, sorry, alpha plus beta 1 x1. Okay, so the third one to the standard.
Let me ask Richard. Richard, so can you use these models to explain quickly what you said? Because I know you can. Okay, I think that the network is. So yeah, you're right. This is the interaction. This is the mediating. So if I remove this one, this x2 from this model, if I remove this one here, this x2 from the first model, I'll get back this. If x2 is 0, okay, then it means that we fall down into this. Then now, if you bring it back, okay, down, you know the behavior of how in the presence of x2, how is x1 behaving? And then in the absence of x1, how is x, in the presence of x2, how is x1 behaving? And in the absence of x2, how is x1 behaving?
Now, do you mean in a larger model where you put all of them with the interaction, or just the second model? Because the second model is to be independent of each other. The beta 1 x1, beta 2 x2.
This second model, imagine the only two variables that are there are x1 and x2.
Yes.
And then you decide to remove x2 from the model.
Yes.
And then you run the model without x2. What you are doing is that you are mediating the effect of x1 with x2. Because you know
if you
x2.
Take out the x2.
Say it again.
You take out the x2 from the model.
You take out the x2 from the model, you run the model without x2. You bring x2 back to the model as it is here.
Yeah.
And then you see whether including or excluding x2 makes any difference in the model.
Okay. I thought many times the independent variables are independent in such a way. If there will be any relationship with the dependent variable, perhaps it will just affect the intercept. The beta will will be the same regardless of whether we add more variables.
Oh, no, forget about the beta, because I could have used any letter for the beta.
Yes, I mean, the estimate, the valid estimate, the coefficient.
Yeah, and I'm saying that the coefficient, I could use any letter for the coefficient. Okay. I could even remove the beta one and call it gamma, and call this one beta, yes, and call this one alpha. Yes. Yes. The focus is on the independent variable. It's not on the beta parameter.
Yes.
Okay.
So I was saying that, for example, wages on experience and education, X1 experience, S2 education. If I take out the whole experience, and I'm just finding, so it comes to the third model, how experience affects education. When I add education, how experience affects the wages.
Yeah.
That's the third model. So the third model, just experience on wages. The second model, adding education experience on its effect on wages. In the first, the interaction between experience and then education on wages.
Very good. So Richard has just put some explanation to what he said also. I know the reason why I'm asking this is that sometimes it's not that clear exactly which is which. I've seen that, multiple times. There's even confounding variables and several other things that people do. But it's important to get the relationship between the two and know. So one of them is when one is there, one is not there. The other one is when both are there separately, but or when both are there together. Okay. So one is there, the other is not there, okay? Or when both are there separately, or both are there together.
Okay.
With that, you are able to capture the relationship between interaction and that of mediating. Okay, so this is a general model. Okay. So in this very example, you will notice that, and this is, we'll come to fix it, but I just want to indicate this. Where's that? Okay, so we made a point of this interaction that be careful not to add too many interaction terms, especially when there are many independent variables. Okay. It has to be backed by theory, basically. You can do interaction between an independent variable and a binary independent variable. So when the thing is binary, it's all right to multiply it with another variable. When one is binary and the other is continuous. You can also do some two continuous variables like we did. But because the time is binary, the time dummy is binary, or it is a dummy, that is why sometimes you can actually apply interaction to the time. If you identify that a particular independent variable is a dummy, that variable can be interacted with another variable to see whether its interaction can make any difference. If it is a fixed effect model, fixed effect, as the name sounds, will remove every time invariant variable, every time constant variable. So you will not get them in the fixed effect model. So anything that is fixed, like race, will be removed from the fixed effect model. Now remember that we've indicated that for this very example, education can be fixed and experience can be fixed. The reason is because they are assumed to be fixed because they will roughly increase by, for example, they will not go to school within a period of time until after 5 years. So within that 5-year period, we consider them to be fixed. But even though we consider education to be fixed, they can now be interacted with the time dummies to see if wages is constant over time or is not constant over time. But in the case of the random effect model, which we shall look at, everything is included. Everything, all the time fixed variables, time constant variables, race, gender or anything, they are all included in a random effect. So this is a general model. We are going to convert this general model to our specific one and write it. This is a formulation. And in this formulation is very important. So the first easiest pathway to panel model is a pooled OLS. That pooled OLS, it ignores the unobserved heterogeneity across the groups or time. So it doesn't even matter. Even though there's panel, it ignores the panel. It assumes that the effect of any of the regressors is constant. And that's not true all the time. So why should you use the pooled OLS? And why should you not use the pooled OLS? Now, if you can remember the OLS itself, okay, it is a consistent thing if the covariance between the errors and the regressors are zero. That is no indigeneity. Okay. That is if the errors are not correlated with the independent variable. So there's no problem there. But if they are correlated, that is if there's indigeneity, and the reason why there's indigeneity is because there are some unobserved factors that are correlated with the regressors. In that case, the OLS will be biased because you will not handle. So if you use the pooled OLS, it's not going to be correct. Whether it's OLS or pooled OLS is the same thing. It will be biased, it will be inconsistent. But we are still going to do it to see the results because this is for comparative purposes. So we're going to use the wage, we use the wage band data and we estimate the equation for this young man. In this pooled OLS, we are going to include education and race. Okay. Race is a dummy, which is Black, Hispanic, and other. But when we get to the fixed effect model, these ones will drop because remember, fixed effect model, anything that is presumed to be fixed is removed from the model. But those that are time varying variables, here we are going to include them. Like experience is time varying, experience square. Union is time varying. Remember, they are changing their unionism. Marriage is time varying because we are assuming that this case will marry over the 7-8 year period. And then we'll also include the time dummies. There we go. So let's estimate the model. This is a general model under the pooled OLS. This is a general. Now, specifically related to our own, this is how it becomes. Watch carefully. How we formulate the model also matters. So this is the log of the wage. Remember, we've logged the wage. So the interpretation will have to be percentages. It's a function of the education. Education is individual specific. Experience is both individual and time varying. Experience is squared to account for quadratic nature of experience. Union is time varying. You remember we said that union, a person can change his union. Marriage is time varying. Of course, it's also individual varying. Ethnicity is only individual specific. It's not time specific. So a person's ethnicity is fixed. And then all the time dummies are here. They have all been added here. In this case, what you want to do is I want to see whether whether wage is changing over time. That's why you have the time dummies there. Whether wage is changing over time. And then you have the error term. This error term is not the composed error. Remember, this is normal OLS, and we are just calling it pooled. The only reason why we are calling it pooled is that we are ignoring the time. So if a young man in 1980 and that same young man in 1987, we are considering them as different young people. So we are not counting the time. We are not going to say that young man is the same young man. We're going to say that they are two different young people. That's what we say. That's the pooled OLS. So we are going to, after formulating this model, we are going to write this model into the R, and then we'll see. Now, we'll do that. We'll do that very soon. But if you are doing the pooled OLS, you should know that you will by all means fall into the problem of autocorrelation and heteroscedasticity. You should know. And so you got to immediately correct for the standard errors. Okay. Unless there is no cluster effect. That you can't tell. So just correct for the standard error. One way you can correct for the standard error is to use the robust standard errors. Okay. In some regression packages, they have simple commands to correct for the standard errors. We have it as well. So we're going to use that. But we want to correct for not only heteroscedasticity, but we want to also correct for serial correlation. So we do it at a go. And the last time we spoke about the newer West. So this is a model. Remember that because you are dealing with panel, you've got to load the data as it is here. So I'm going to load the data here. So this is the data. First, you have to invoke the panel linear model package in this command, the panel linear model package. I have just invoked that. Load the data. Let me see whether this is the data. Yeah, this is the data. You can see the data nicely showing down here. Now, the data is loaded. Let's look at a bit of summary statistics about the data. So these are basic summaries. The first summary is this. And you can see it's a fake summary. So for example, my interest is on the wage here. So you can see that we are able to get the mean wage, which is 5.91, but we are interested in the log of the wage. So the mean log of the wage is 1.65. So you're able to get a few statistics about the data. That's the first thing. But it doesn't give you a lot of statistics. It doesn't give you a lot of statistics. What it does is that it gives you few of them. So you have to load a package called library pastex. This library pastex will give you more, descriptive statistics. So I'm going to run that here. There you go. You can see that this one gives you a lot. Huh? For example, it gives you the values. It gives you those that are not available. It gives you the minimum, the maximum, the range, the sum, the median, the mean, standard error of the mean, confidence interval of each variable, standard deviation, the variance and the standard deviation. But I'm more interested in the last one, the coefficient of variation. Now, that one is usually nice when you're dealing with non-parametric data, the coefficient of variation. So that's another way to get the summary statistics. You can also group the variable. You can also get another summary statistic, which is really good. To do that, you invoke a package called library site. Library site. This is a package in blue here. Then you now type describe wage pan. The wage pan is the name. So library site, they use describe wage pan. Okay, this one will give you more descriptive statistics, the minimum, the maximum, the range, the skewness, the ketosis, and all of that. Let's see. So that is, but let me just push this one here and see. So that's it here. So you can see that we are getting a lot of information about the data. And as for interpreting these ones, you should be able to do that by yourself. Then the next thing is you can also describe groups. So let's say that you want to describe by virtue of the year, like when you pick each year, what is the descriptive statistics for each variable in each year? You can use describe by year. Okay, and this is it. So watch this one. This one is only giving you the situation for 1987. Okay, This one here is giving you the situation for only 1988. 1988. For each year, you're able to get it for each year. For each year. You follow, Godwin?
Yes, I'm following. I'm even running.
The next one is to check each variable according to whether they are married or not married. So once you run this, watch it. So this one is not married. So for not married, you're able to get the mean age, the mean wage. So if you take the nominal wage for the married, this is it. So you will notice that the average wage of those that are not married is $5.43.
Oh.
And let's go and check those that are married. The average wage for them is $6.54. So when you are married, you seem to get some, on average, get more income. So you are able to get descriptive statistics by groups as well. You can even get descriptive statistics according to experience and according to groups as well. So there are so many things that one can actually do with that. So if you look at this one, yeah, 1980 descriptive statistics, basic one, 1981, 1982, each one of them you are able to get it. This is how you handle the initial thing of the data. This is all basic. We have not even come to the pooled OLSO. These are just basic. But there's more you can do. Maybe you want to look at the correlation. You can also do that. You can also extract the dimension of the data. So this command can give you the dimension. I did all of these ones. So the dimension will tell you whether it's a balanced or unbalanced. Okay. Now, this one, it is telling you that it is unbalanced. Okay. But we know that it's balanced. Okay.
So how come mine balanced?
Sorry?
Mine says balanced.
I don't know, to be honest. I don't know, sometimes the information will be solar because you can see, because it's taking some T-1 from the time period or something, I don't know. Because when you look at this one and that, they are all the same, so it should be balanced.
Yeah.
But when you are running the panel model itself, that one, it will tell you clearly that it's balanced.
Okay.
The most important thing here is exploratory data analysis. It's always good to get a feel of the data, explore a bit of the structure of the data. So we're going to do something called co-plot. And by the way, sometimes the results will not show because it's so long. So we use a package called library Gingin plot. It's supposed to be a graph. So I have to first of all give it a chance to show. Okay, fortunately you got it. So this is a graph of the data. So what does this tell you? What does this really tell you? So you notice that this is a log of the wage for each year. You can see that the data is very nucleated together from 1980 to 1986 for each very year. The data is kind of nucleated, very thick. Those ones on the edges are supposed to be few sort of outliers away from the main data, but the number of outliers are not that many. Okay. Here are the ones on the edges, singularized in that regard. So it's able to give you a feel of the data, whether outliers are bigger issues or they are not a bigger issues. Now, let's check whether there is a lot of heterogeneity across the individuals. That is whether these individual boys, whether they differ significantly among themselves or not. Okay, so so this is it. Come on. Let me run it again. Good. So remember, this is a data set of lots of observations. So when you look at this, it draws 95% confidence interval around the mean, and it tells you whether the data exhibits a lot of heterogeneity or not. Now, are there any unobserved variables that change over time or don't change over time? Well, if you look at it again, majority of them, if you check it, the black area, majority of them are all around the center. So it does appear that this is just graphical. It does appear that maybe there is not much heterogeneity. You can see that clearly from here. With 545, there is a kind of an increasing trend, of the wage over time, without much deviation, from the center, without much deviation from the center. So all of these are here. So these are just initial things to do before you run the data. It's just to give you a feel of the data. Now let's go and run our pooled OLS.
Okay.
This is it. This is a pooled OLS formulation. Now let's run the model. This is a command we use to run the model. You're going to run the pooled OLS model, okay? A one-way individual effect pooling. I'll show you something. This pooled OLS model, we are using the PLM package, but you can also use the OLS package because pooled OLS is actually OLS. But because the rest, we are going to use PLM, panel linear model, we are going to start with using it straight away from here.
Okay.
This is the dependent variable, which is a log of wage. It's dependent on education, experience square, union, married, and then ethnicity or race. And then you can see that you have time dummies, all of them. But watch this. The name of the data is wage pan. Watch this. The index is the ID and the year. And here is the most important one, the type of model. That is where you choose pooling. The pooling here means that you are using pooled OLS. Pooled OLS.
Right.
Okay. So that is what you would change when you are now using other panel static. Everything you are doing is static panel models. Other static panel models. This is where you change that one. Okay, so we're going to run that. And then see the results down here. There you go. So you see the results down here. Now, do you realize that now it's telling you that it's balanced? I told you that we should wait.
That might give me a balance from the beginning when I run that command.
Oh, okay. That's good. So it's balanced. Now you get an estimate, as it would always have been. You get the estimate for each explanatory variable. And then on the far right, you know whether it's significant at what percent or not on the far right. The total sum of squares is there. The adjusted is 19%. And then the F statistic is significant. Okay. But we have some questions to ask here. And we will do those interpretations next time when we meet. What I will urge you to do is go and run the others, looking at the codes, run the others. Then we will use those others. When we come to the interpretation, we'll use that. But the next important thing is to answer the research question, just based on the pooled OLS.
Okay.
Once you have the results, that's it. But in real life, you will not only use pooled OLS. So we'll come and answer those same research questions using the other model subsequently. That brings us to the end of the entire topic.